Hello, and welcome to this video lesson on probability. In this lesson, we'll discuss Venn diagrams, complements, two-way frequency tables, union and intersection, and the addition rule. First, we denote the probability of event A occurring by the probability of A. As a simple example, say the probability it will rain tomorrow is 40%. What is the probability it will not rain tomorrow? Well, given that the probability it will rain is 40%, the probability that it won't rain must be 60%. These two events are said to be complementary. They give the complete set of possibilities. Either it will or it will not rain. When dealing with probabilities of complementary events, the probabilities will always add up to either 100% or, if just in straight decimals, 1. So the probability of event A not occurring is written as the probability of not A, is the complement of the probability of A. An event and its complement always adds to 1. So we can write the probability of A plus the probability of not A equals 1. More notation. The probability of A or B. It's also written as the probability of A union B. And that's everything that's inside circle A, as well as all the elements inside circle B. So that would be x plus y plus z in this picture. Anything in the yellow, or the green, or the blue, just make sure you don't count the y twice, the intersection region. So in this picture, the probability of A or B, again the probability of A union B, would be 0.4 plus 0.2 plus 0.3, which is 0.9. The probability of A and B is the probability of A intersection B. And again, it's just the intersection of circle A and circle B. And that would be Y. The intersection, think of it as and. It must be inside circle A and inside circle B, which again would just be the overlapping region between the two circles. So in this example, the probability of A and B, or the probability of A intersection B, is 0.2. Let's look at this example. Suppose the probability of A is 0.23 and the probability of B is 0.31. And furthermore, the probability of A and B is 0.12. Find the probability of A or B. Well, a Venn diagram is a nice visual. It helps keep track of where all the members are. So we know the intersection of the probability of A and B is 0.12, which I've already labeled here. Next, if the probability of A, the probability of event A occurring is 0.23, but I already know this part of the probability circle is 0.12, then the part over here in yellow must be 0.11. That 0.11 is the probability of A occurring and the probability of B not occurring. Similarly, over here we have the probability that B occurs and A does not occur, and that's 0.19. The 0.12 is the probability that they both occur, and since all four of these numbers have to total 1, which is the entire universe or sample space, then the probability of neither event A or event B occurring would be 0.58. We really didn't need to find that though to answer the question. Find the probability of A union B. It's just the sum of those three numbers, 0.11, 0.12, and 0.19. It's the yellow plus the green plus the blue. Now look closely down here at the bottom of my screen, because I could have taken, without having to draw a whole Venn diagram, I could have taken the probability of A, which is 0.23, which is the entire circle on the left, that includes the yellow and the green, plus the probability of B, which was 0.31, which is the circle on the right, which includes the blue and the green again, minus the probability of the intersection. Because the green was counted twice, I have to subtract it off one time, because remember, we don't want the green counted twice. I don't want 0.12 in there twice. I don't want to double count it. So we have to subtract it off. That's called the addition rule. The addition rule simply states the probability of A union B is the probability of A, which is the entire circle on the left, plus the probability of B, which is the entire circle on the right, minus the probability of A intersection B, because otherwise the green, the overlapping region, gets counted twice. That fixes that. Venn diagrams and two-way frequency tables. Let's look at this example. Of a group of 50 people, you are told 18 of them have blonde hair, 20 have blue eyes, and 12 have both blonde hair and blue eyes. How many people have neither blonde hair nor blue eyes? Sounds like quite the mind bender. Well, again, a Venn diagram will help keep track of all of our 50 people. I have a circle that I created for blonde-haired individuals that overlaps a circle for blue-eyed people. We know that 12 of them have both blonde hair and blue eyes. So that must be the overlapping region. The area in gray represents the 12 people that have both blonde hair and blue eyes. Next, I can figure out that 6 blonde-haired people do not have blue eyes. Because if 18 have blonde hair and 12 of the blonde-haired people have blue eyes, there must be 6 additional blonde-haired people that have not blue eyes. Similarly, we were told 20 people have blue eyes. Well, if 20 of the blue-eyed people have blonde hair, there must be 8 of the blue-eyed people that have some other color hair. And finally, since we know that the group totals 50, 6 plus 12 plus 18 is 26, plus 24 gives me my complete set of 50. How many people have neither blonde hair nor blue eyes? That's this group of 24 that's outside of both circles. If you're outside of this circle on the left, you do not have blonde hair. If you're outside of the circle on the right, you do not have blue eyes. The 24 here are outside of both circles, so they do not have either blonde hair or blue eyes. A two-way frequency table. It's similar. It's an alternative to Venn diagrams. What you do is you take your possibilities. In this case, we have blonde hair, so I made that my first column, and non-blonde hair is the second column. We have blue eyes, I made that my top row, and then other than blue eyes, so not blue eyes, I made that my second row. Along the far right and along the bottom are my totals. Now, I fill in what's given to me. I know that 12 people have both blonde hair and blue eyes, and that a total of 18 people have blonde hair. I know a total of 20 people have blue eyes, and I know that there are 50 people in the entire population. Next, I get these red numbers, because if I have 12 blonde-haired people with blue eyes, then I must have 6 additional blonde-haired people that do not have blue eyes. You can see that over here in this Venn diagram. And 12 plus 6 equals the 18 total blonde-haired people. Meanwhile, looking at the blue-eyed individuals, if 12 of them have blonde hair, 8 of them must not have blonde hair, and you can see that again in the Venn diagram, for a total of 20 blue-eyed people. Along the outside edge, we have 20 plus 30 equals 50, and along the bottom row, we have 18 plus 32 equals 50. Next, our last number to get is to fill in this one empty box, and that must be 24. Either 6 plus 24 equals 30, or 8 plus 24 equals 30, or the sum of these 4 boxes inside here are your complete set of possible outcomes. You can see all 4 of these numbers in this Venn diagram. It has to total 50. If I already had 26 in these 3 boxes, there had to be 24 left in this box. So there are lots of ways we could get this 24. And by the way, that's what we were looking for. Notice the intersection of this column and this row. Those 24 do not have blonde hair, nor do they have blue eyes. So 24 people in the group of 50 have neither blonde hair nor blue eyes. Same problem, but I could have done it with the addition rule. We could use the number of blonde-haired people or blue-eyed people equals the number of blonde-haired people plus the number of blue-eyed people minus the number of people that have both blonde hair and blue eyes. Substituting in our numbers, the number of blonde-haired or blue-eyed people would have to be 18 plus 20 minus 12, which is 26. But remember, we wanted the complement of that. We wanted the people who were neither blonde-haired nor blue eyes. So if 26 have either blonde hair or blue eyes, then it stands to reason that 24 would have neither blonde hair nor blue eyes. Of a group of 50 people, you are told 24 have brown eyes, 17 have brown eyes and brown hair, and 29 have either brown hair or brown eyes. How many people have brown hair? You could pause the video and give it a try, but here we go. Again, starting with the Venn diagram, I have brown hair on the left, brown eyes on the right. We have 17 that have both. Filling in these numbers, I would have to have 7 brown-eyed people that do not have brown hair. Because remember, we have to have 24 brown-eyed people. If we had 17 of them here, there must have been 7 out here. Furthermore, we knew 29 have either brown hair or brown eyes, so that's the total of these 3 numbers. Once I have these 2 numbers totaling 24, this had to be 5. That way those 3 numbers total 29. And if we have 50 people total, there must be 21 out here. Now, I really don't need this 21 number to answer the question, how many people have brown hair? Well, it's everyone inside this circle, which is 22. Same question. I could have again used the addition rule, plugging in the values that I know. I would have once again come up with 22 people for the number of people that had brown hair, which would have agreed with our table from the previous slide. Of the 10 cars at a dealership, say 3 are convertibles, 3 are blue, and 5 are neither a convertible nor a blue car. How many cars are both blue and a convertible? Well, let's do this one by a two-way frequency table. I set up convertibles in the first column, non-convertibles in the second column. I set up blue cars in the top row, non-blue cars in the row beneath it. Filling in the numbers that we were given, we know that there are a total of 3 blue cars. That's where I put the 3. We know that there are a total of 3 convertibles. That's where I put that 3. We also know that 5 are neither a convertible nor a blue car. So I put the 5 in the intersection of not convertible and not blue car. Finally, we know there are 10 cars at the dealership. Next, I find that these 2 numbers have to be 7 because 3 convertibles plus 7 non-convertibles must be our 10 total cars. Looking at it another way, 3 blue cars plus 7 non-blue cars must give us our 10 total cars. Next, I can find these 2 values. How? Well, 2 plus 5 is 7, and over here 2 plus 5 is 7 across that row. And once I get those 2's, then it's easy to get this number. 1 plus 2 is 3, or 1 plus 2 is 3. That's the answer we were looking for. How many cars are both blue and convertible? And that would be 1. Only 1 car is both blue and a convertible. And here they were. You'll notice 3 convertibles, 3 blue cars, and 5 that are neither blue nor convertible. Only 1 car was a blue convertible. For our final example, let's say the probability of A is 0.3, and the probability of B is 0.21, and the probability of A or B is 0.41. What's the probability of A and B? Seems pretty challenging. The Venn diagram is my least favorite way to go on this problem. I'll explain why, but then we'll go back and we'll answer it anyways. But the 0.3 for the probability of A is the total between the yellow and the gray. The problem is I don't know how to split it up here. The probability for B is the circle on the right, has to be total of 0.21. Again, I don't know how much to put in the gray, how much to put in the blue. Finally, the probability of A or B is 0.41. That's the total of the yellow, the gray, and the blue. That seems like an awful lot of math to try to figure out which numbers are going to go where. There is an easier way, and we can answer it with the Venn diagram, but we'll come back to that. A two-way frequency table is an easier approach to see. So I set up the probability of A in the first column, probability of not A in the second column, probability of B in the top row, probability of not B in the second row. And I was given the probability of A is 0.3, so I put that here. And the probability of B is 0.21, so I put it there. And now I'm holding off on the probability of A or B. That's 0.41, because the probability of A are these two boxes, or means add the probability of B, which would be those two boxes. So really that's the total of those three boxes. Well, remember, the total probability has to be 1, so this number should be 1, which means I can figure out these numbers next, 0.7 and 0.79. Now, once again, these four numbers have to total 1, my grand total over here. Well, if these three boxes total 0.41, then this box has to be 0.59. Just a little subtraction gets you that. And now I can figure out these two boxes easily enough, because what plus 0.59 is 0.79, that must be a 0.2. And what plus 0.59 is 0.70, that must be a 0.11. And once I get those, I can quickly get this one, and that's 0.10, and that was the answer I was looking for. What's the probability of A and B? That's the intersection of probability of A with the probability of B. So that's my answer. Had I used the addition rule, the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. This is the easiest way to do this problem. Watch, once we fill in the numbers that we were given, there's only one unknown. We add this over to this side and subtract the 0.41 over to that side, and we quickly get the answer. Probability of A and B is 0.10. Now, here are the values filled in the Venn diagram. Probability of A and B is 0.10. The probability of A not B is 0.20. You'll see that there. The probability of B but not A is 0.11. You'll see that there. And the probability of neither A nor B is 0.59. You'll see that there. But how could we have gotten that with the Venn diagram? Again, this would be my last choice. But what I would start with would be the 0.59. Because if the probability of A union B is 0.41, these three numbers is 0.41 for a sum, then the number in the box outside the circles must have been 0.59. 1 minus 0.41. Once we have that, the probability of A was 0.3, so the probability of not A, its complement, must have been 0.7. Everything outside circle A must total 0.7. Well, since these two values, which I wouldn't know at the time, are inside the probability of A, then these two numbers are the only two numbers that would be outside. So they're the probability of not A. Since I already know this was 0.59, this would have had to have been 0.11. Similarly, if you know the probability of B is 0.21, the probability of not B, 1 minus 0.21, would be 0.79. Again, probability of not B is everything outside this circle on the right. So it'd be this number plus this number. But we, again, already knew this was 0.59. So this must have been 0.20 here in yellow in order to give us a total of 0.79, which is the complement of the probability of B. And then finally, once we'd have those three numbers, knowing that all four numbers total 1 would leave me the overlap, the intersection probability of A and B to be 0.10. The most difficult way is with the Venn diagram. The easiest way is with the addition rule. Well, there you have it. I'm Murray Wright. Thanks for watching.